Okay, today we're going to continue with game theory, and in particular we're going to have two applications, one for the games, simultaneous games, and the other one for the and the other one for sequential games. Then further we proceed to repeated games and discuss two major definitions then, and that would wrap up today's lecture. This would finish the third lecture, and we'll have one more to finish game theory. So, any questions up to now? Everything fine? Great. So today we're going to discuss start with two applications of what we studied by now. But remember, up to now, we studied two major equilibrium concepts. One is Nash equilibrium, and the other one is subgame perfect equilibrium. Subgame perfect equilibrium is a subset of Nash equilibrium, but it is more reasonable. So it is more applied to games that are played sequentially, or somehow they're dynamic. And that would help us to eliminate some of the Nash equilibria which are not credible. We taught last week how to identify each subgame and how to find subgame perfect equilibrium. In fact, subgame perfect equilibrium is the sequence of Nash equilibrium from downward to the up of the game for each subgame. So if you find a Nash equilibrium in each subgame of the game and start from the end of the game and go upward, that would give you subgame perfect equilibria. Sometimes we have one, sometimes we have more than one, but doesn't matter. As long as they satisfy the argument we discussed, there will be an SPE. So let's somehow go back to the case of simultaneous games and Nash equilibrium and remind ourselves one of the first Nash equilibrium that was studied by economists well before we know game theory and well before we know the concept of mutually best responses. So that is called Cournot duopoly. You obviously know what Cournot duopoly is, but if you don't worry, we go through it from the beginning. So the Cournot duopoly usually refers to a case where there are two firms and they compete with quantities. So they simultaneously choose in the amount they will produce, and then the market price will be adjusted based on their quantities. Let me give you an example of, for instance, Cournot duopoly. Suppose Apple and Samsung compete with quantities. You know that the firms can compete with prices as well. So, but just for the moment, suppose Apple and Samsung compete in quantities, and there is a market demand for smartphones, and these are the only two companies that are producing smartphones. And so they know that there is a market demand for this product. They each set a quantity at a time, and then they'll sell their product. So what is the problem here, or let's say what is the incentive, or let's say strategic behavior here, is that if one firm, for instance, decides to produce a lot of the smartphones, then the price will drop and both firms will simply lose. So you cannot simply decide to maximize your profit individually. Whatever the choice of the other firm is would affect your choice as well. That's true for the other firm. Whatever you make whatever you decide about the quantity will affect the other firm's profit. And the obvious thing is you cannot both choose your personal or individual maximization profit point, because this is not necessarily the case when your guys interact with each other. You're dealing with a market demand rather than individual demand. Here, in a very simple example, we try to somehow formalize what I just said. Two firms, 1 and 2, produce a homogeneous good and choose simultaneously their product, the outputs. Of course, Apple and Samsung is not the best example because their products are not completely homogeneous. Maybe, let's say, Coles and Woolworths and potatoes. Okay, amount of potatoes they produce and sell. Suppose they're the producers of potatoes. Or let's say there are two farmers producing milk. So milk is also something that you can consider homogeneous when there are two farmers. Those are better examples. So they choose a quantity, QI, and they sell their products in a market that has a market demand of P of Q greater than 0. So when we say Q is the market demand, it's equal to the sum of Q1 and Q2. So each firm's quantity will go to a market, will be added by the other firm, and then define the price based on this function. Let CI, QI denote each firm's cost function. And then we can somehow define the profit functions as follows. I use UI here to somehow show you that this is similar to the payoffs that we discussed before in games. But usually, in firms analysis, we use term pi for profits. So it doesn't matter. It's just a notation. But we use UI here just to be somehow consistent with the previous notation in terms of the payoffs. Here, remember that each firm's payoff is basically their profit function, okay? So the numbers that we had in the boxes previously, say 2, 4, whatever, those are a profit of a firm here that comes from this formula. What is this formula? Their revenue minus the cost. Revenue is price times quantity minus the cost. Of course, we usually simplify these examples if you want to give it to you in an exam questions. Like, for instance, we make an assumption for the demand function. The simplest way here is just to assume the demand function is 1 minus Q. And remember, this Q is the sum of Q1 and Q2. Okay, it's a market Q, not individual Q. And we also assume here that the cost function is simply CQI, a linear cost function. Now, you can obviously write payoff function for both firms in terms of this equation and that equation. Just need to substitute them there. Then you obviously find something which is a function of both QI and QJ, where QJ is the quantity of the other firm. So what you can see here is that the profit function or the payoff function of firm I depends on not only their own product, but also the quantity of the other firm's product. Okay? Now, there are a couple of things that we want to ask you to do here. Define first RI as the reaction function of firm I. What does that mean? It means that how would I react to the quantity of choice of the other firm? So if other firm chooses 2, what would I choose? Okay? So obviously, my interval is choose anything from 0 to infinity. But that is not a reaction function. Reaction function maps exactly one quantity to every choice of the quantity of the other firm. So define that. The question asks you to first derive both players' reaction functions and graph them, show the unique Nash equilibrium, and then use the graph to use iterated elimination of strictly dominant strategies. Now let's see how we can solve this problem. To draw best responses, so let me first define the major difference of this problem compared to what we learned up to now. The biggest difference is that our payoff function here is continuous. Okay? So our payoff is a function rather than a number. Previously, when I gave you an example like this one, you can see the payoffs are just numbers. Okay? So if you take any action, then you have an exact specific amount for your payoff. But here, we have a function, a continuous function of payoffs. Now, can anybody tell me what are the actions here for each firm? The choice of quantity. So is it again 1 or 2 actions? So previously we had, for instance, right and left. But now the choice of quantity is also a continuous set. So therefore, the set of actions are also continuous. So I cannot draw a tree game like previous, because previously I had left or right, confess or not confess, derive or not derive, so something like that. But here I have the set of actions are the choice of quantities, which is continuous. You can choose any number between 0 to infinity for your quantity. And therefore, the way we draw the game before is not applicable here. That's why we need to go back to our original way of finding best responses, and that is profit maximization. or first order conditions. So differentiation, in other words. Now, having said that, we know that the best responses are no longer a simple strategy of a player, for instance, left versus right. We know that the best responses here are functions. The question defines the best response as a function Ri, but now how can one simply find it? As I told you, Korno basically found this game well before the Nash equilibrium and game theory were somehow formalized as we know it today. How did they do it? How did he do it at that time? Simply by theory of incentives. I mean, it's very easy to just think of the incentives of the firm. I'm trying to choose a quantity, and what is my best response given the other firm's quantity? So what I will do in my profit function, I act like the other firm's quantity is fixed, and then I find a function that gives me a quantity for every choice of the other firm's quantity. How would I do that? When I assume the other firm's quantity is fixed, I can differentiate the profit function based on my own quantity, which is the variable here, because I cannot affect the other firm's quantity. I can also only choose my own. So I can differentiate the profit function based on my own quantity, put it equal to 0. That is the first order condition maximization problem. And whatever I get is a function which is a relation between my own quantity and the other firm's quantity. But now the difference is that these quantities, for me, are my best responses to the choice of the other firm, okay? Because it went through my maximization problem. So given any Q2, my choice of quantity, which is the result of this problem, is the best profit maximizing choice of me, okay? Now let's see how one could do it in this example that we just gave you. I need to substitute first from the demand function that we have there, which is 1 minus Q1 minus Q2. I just substitute this with that. And then the profit multiplied by Q1, because that will be the whole revenue, price times quantity. And then minus by my cost, which is C times Q1, the cost function. So what I need to do from now on to find the R1 is to maximize this term, let's say this term, for any Q2 by choosing an R1. So now from now on, instead of Q1, I say R1, reaction function of firm 1. So again, here is a little bit of alert in terms of notations. Some textbooks use Q1 star rather than R1. So do not be confused. R1 is just a choice of quantity for firm 1. It's not a different variable. It's just, but those choices that are best responses to the Q2. Okay? Some textbooks use Q1 star. The reason we use R1 here is that we will have an equilibrium outcome, which is the Nash equilibrium. We use Q1 star for that purpose. Some textbooks use Q1 star for the reaction function and Q1 double star for the equilibrium. Okay? So these are just notations. You need to use one notation for the reaction function and then one notation for equilibrium. So if you want to somehow see what would be the similar thing that we had in previous, this is simply stars and deltas we put on each boxes for firms, for players. You remember that we put a star in a box that was best response of a player. So this R1 is exactly the same thing. But because the payoffs are continuous, R1 is also a continuous function. Okay? Now, you know, I mean, of course, many of you know how to maximize a function like that. If you have difficulties doing that, just let either me or your tutors know. These are the mathematics that you need to know to be able to do courses like this. This is just the first order differentiation. But some of you may have done it long before. You may get used to it after we do it a couple of times. But don't be somehow ashamed of not knowing this stuff. Just let us know privately, either in consultations or after the classes. Then we'll be able to help you to catch up. So how do we do that? We simply differentiate with respect to R1. I mean, again, I could use Q1 rather than R1, but what I did, I just substitute R1 with Q1 to just differentiate any choice of Q compared to those that are just best responses. Any choice of Q is between 0 to infinity, but R1 are only those that are best responses. So now when you differentiate this function with respect to Q1 or R1, then that will be the result. How come? Let's do it once to make sure that we are all at the same page. So what I need to do is just substitute R1 into Q1 and then multiply both sides of this. You get R1 minus R1 to the power of 2 minus Q2 R1 minus C R1. Okay? Now, if you want to differentiate this with respect to R, it will give you 1. So U1 with respect to R give you 1 minus 2R1 minus Q2 minus C. That's exactly what we have here. Okay? And as you know, for profit maximization, when we put that equal to 0, the amount we get will be the maxima or the global maxima of this profit function. Given that the profit function here is concave, that will be the global maxima. So we put this equal to 0. We keep R to the left and take everything else to the right. That will give me R1 equal to half times 1 minus Q2 minus C. Okay? Am I right? And be very careful not to make any mistakes in terms of negatives and plus. I think I'm right. That's, yeah. Yep. So that would be the reaction function of firm 1. What does that mean? It means that for any choice of Q2 for the other firm, let's say 100 for instance, and 100 is a big number for this example, but let's say, for instance, half, let's suppose the numbers are in million, 500,000, then you get 1 Q1. Okay? That is what we call the reaction function. So now I know what are firm 1 responses compared to the choice of firm 2. Of course, we can do the reverse thing for the other firm, and we get another reaction function. The intersection of these two functions would give us the mutually best responses or the Nash equilibrium of this game. Okay? So hopefully this game is symmetric. What I'm going to do, I can simply get the other firm's reaction function by substituting. Now this max, don't be confused with that. It's not the rocket science. It simply says that if the other firm has a choice of quantity which is too large and makes the choice of this firm negative, then it has to be 0 because you cannot have negative quantity. Okay? Why is that the case? Because we know that the demand function are downward sloping. So at any point, if the other firm suddenly act irrationally and produce too much of a good, this firm's choice could become negative to somehow balance the stuff. But in reality, we cannot have negative quantities. Therefore, that's how we write functions of quantities and prices. We write max of 0 and the function. Okay? This means that anything below 0 will be considered as 0. Okay? I remember that, yeah, some people do not like this way of max of 0 and something. And you will see in some textbooks they assume that this is a case and quantities cannot become 0. Therefore, they simply write the reaction function equal to half of 1 minus Q2 minus C. I mean, in the exams, we try not to be very picky. So if you even write this, you're probably going to get the full mark, unless you explicitly mention that. Okay? So what does that mean? In other words, I can write this for every Q1 greater or equal to 0. That would exactly say the same thing. Okay? I mean, there are different ways of representing a mathematical notation. Some people, they don't say this because it's obvious that a quantity cannot be negative. Okay? So, any question here? Great. Now, for the moment, just ignore the max. This is the right way, very correct way of writing it, but even if you don't, it doesn't bother much. It wouldn't bother much. Now, as I said, the game is symmetric. I can write the other firm's reaction function by just substituting Q1 and R1 and R2, and Q1 and Q2. So now this is the choice of quantity of firm 1, and this is the best response of firm 2. Now, as the question says draw them in a diagram. Now, if you would draw these in Q1, Q2 diagram, obviously R1 here means Q1 and R2 means Q2, but best responses. So you can see there are two downward sloping lines. One is steeper and the other one is less steeper. Which one is steeper? Obviously, if you look at the slopes, you can see that in a diagram where Q1 is in a vertical axis, the slope of this guy is minus half, and the slope of this guy is 2, because you have to reverse it. When Q1 is in the vertical axis, then this Q has to come to the left if you want to draw it. If you're an expert, you can draw it in the reverse way as well, but usually the way it works is that you draw a function y equal to a plus bx, and this is x, and this is y. Okay? Here in our example, y is Q1 and x is Q2. So therefore, this reaction function is the steeper one for firm 2, and the less steeper one is for firm 1. There must be an intersection between them, because one is steeper, the other one is not steeper, and the intercepts are different. Therefore, and there's only one, because both functions are strictly decreasing. There won't be more than one intersection. And that intersection is our Nash equilibrium. Now, how do we find that? Again, this is a mathematical technique, very easy one, not that difficult. Don't get insulted when I say very easy if it's not easy for you. I mean, when I say very easy in terms of the whole knowledge of mathematics, that's very easy compared to many other stuff. How do we do it? We simply, when we have two lines and we want to find the intersection, we substitute from one line to the other one. Okay? That's what we do. And that's how we find the intersection. So these are what we call the Nash equilibrium of the game. And how it works is that we write Q1 star, and now we substitute Q2 star from the best response of firm 2. So this is exactly the best response of firm 2. Okay? Now, if you can see, we have a function of only one variable, and that's Q1 star. And if we solve that, we get Q star. That gives us Q1 star equal to 1 over 3 times 1 minus C. Again, due to symmetry, the same thing will happen if you substitute the players. And instead of putting reaction function of firm 2 into 1, putting reaction function of firm 1 into 2, you'll get the same thing for Q2. Therefore, this will be the Nash equilibrium of the game. Okay? Any questions? Great. Now, having said that, the question tells us to use the graph in 1 to apply iterated elimination of strictly dominated strategies. So now we know the concept of equilibrium and how to define it. We know that this Nash equilibrium is even stronger than we thought. It is IDE as well. Now, we need to show it, of course, it is IDE. How do we show it? We know how IDE works. For IDE, we start to eliminate dominated strategies, and we do it one by one for firms until we get to only one remaining strategy, and that's what we call the IDE. We know that every IDE is NE, so therefore the IDE we find here will definitely be the NE we already found. Now let's see, how do we do that? Simply draw two lines, one vertical to the horizontal axis, the other one vertical to the vertical axis. So now look at these points. Look at these points. I mean the one on top. Can we say they are strictly dominated by these points? We can, because if you look at that point, from there, firm 1 would not react to any numbers below because it gets to 0. So anything below 0 will be negative for firm 1. So firm 1's action will be fixed after this point. Now, firm 2 should not react to those, meaning that if firm 2 reduces their quantity because of an action that firm 1 would not take, they will be dominated because they'll simply reduce their profit while the other firm would not react to it in any way. So therefore, these points are better than these points, so we can eliminate them. The same thing is true for the other firm. I mean, I could start this argument from this firm, which was a bit easier, but the same is true here. We can say these points are strictly dominated by these points. Or I mean, it's better to say this point. But anyway, so when they are all strictly dominated, you can eliminate them. Now, you end up with a much smaller set of points. Again, you need to draw two vertical lines, one from the intersection of here and the other from the intersection of here. So then again, with the same argument, you can show these points are dominated by these points, and these are dominated by these points. Do that again and again, and only one point can remain from this iteration, and that is the Nash equilibrium of the game. Okay? So this is, I mean, the reason that we show you here this example is just to show you that this Nash equilibrium is very strong. And maybe that is one of the reasons that Cournot found it in 1800, well before we know what is equilibrium in games and what is game theory as we know today. So we are done with that example, and that basically tells you how to find a Nash equilibrium when there are two firms in a duopoly Cournot competition and they choose their quantity when they compete. So what you need to be very careful here for exams is that first read the question and make sure what kind of competition we're dealing with. Either this is quantity competition or price competition, okay? And I used to give, you can see it obviously in the library, I used to give an exam question, final exam question, when instead of quantity competition, there were price competition, okay? And now the choices of firms are prices. Firm 1 chooses P1, the other firm chooses P2. In that case, it is more applied to Apple and Samsung because they are not homogeneous products, but in some sense they are substitutes. So if, for instance, Apple tries to change the price of iPhone to $10,000, their demand would reduce and this demand for Samsung would raise because people go buy Samsung, which is cheaper. So therefore, they compete in prices. Another very good example of price competition is also petrol stations, firms that choose their prices in petrol stations. For instance, say 7-Eleven and Shell, they compete in prices and people choose the cheaper. There, obviously, they have homogeneous products, but for the Apple and Samsung, they are not entirely homogeneous. They are substitutes, but different products. So one can change this to a price competition rather than quantity competition. And you need to be very careful when you read the question before you start solving it. I think the year that I gave that price competition question in the final exam, many students decided to somehow differentiate with respect to quantities and found the optimal quantities, found the Nash equilibrium. They all thought that they did the right thing, but they would get 0 because it wasn't a quantity competition game. It was a price competition. And the mistake they would do is because they would use Q1 and Q2 and then everything will be ruined, okay? So don't do that. Be very careful. Now, this is how you can change the simultaneous gain from quantity to price. But there's another way to change these games, and that basically is to change the timing of the game. Okay? For instance, one very famous equilibrium constant that we know from duopolies is a Stackelberg duopoly. That is where players move sequentially. Suppose there is one grocery shop in a town, and they choose to, for instance, have X number of potatoes in the shop, and the other grocery market decides to enter the market, and they'll choose how much potato they'll sell. You may first see that this wouldn't matter, but it will matter. It will matter. It changes the reaction functions and best responses of the game. Very similar to what we had previously. I mean, in the very simplest first game that I showed you, example number 1, when we changed it to a game of 2 steps, you saw how the game changed. So when you observe the quantity of the product, when you buy it, you will obviously respond differently compared to a case when you have no idea about the quality of the product. That's the same here. So when firm 2 decides to choose their quantity, if they already know what is the quantity of firm 1, the game would be totally different compared to a case where they move simultaneously and they cannot observe each other's quantity. So that's what we call the Stackelberg duopoly. Now suppose the same game in example 15 is now played such that firm 1 moves first and sets quantity 1, and then firm 2 observe Q1 and choose Q2. Now I want you to find SPE, of course, because this is a sequential game. Remember that this SPE is necessarily an NE, but we call it SPE because it is an SPE and is somehow a more or a stronger term to use. Sometimes one may ask you to just simply find the NE. Don't get confused with that, because the SPE is necessarily an NE. But you cannot do the reverse. So for the Corno game, the Corno game is sequential, simultaneous. Therefore, nobody would ask you to find the SPE there. Now, the SPE in this game is going to be found as follows. So firm 1 moves first, firm 2 observes the quantity of firm 1, and then chooses its quantity. Let's try to draw a tree game of this game. As I told you, it will be very difficult, but it will look like something like that. So firm 1 decides to choose Q1. Let's call this Q1. And we usually use the following way. So if I do this, this means that these actions are somehow continuous. So from 0 to infinity. And then firm 2 chooses the same thing, 0 to infinity. Obviously, for each of these, we have a U1 and U2 given by the profit functions that was defined before. So the difference between this game 3 and the other game is that if I wanted to draw the same thing for the other game, I had to somehow, it's difficult because, there are infinite number of information sets here. I had to somehow have a dashed line here, meaning that all the 2 information sets are it's just one information set, and they're infinite decision nodes for the simultaneous game. But here, for this game, I don't have to do that because it's sequential. So therefore, firm 2 observes firm 1 action before they choose their quantity. Now, if I want to find SPE, the somehow procedure is similar. I need to use the backward induction. What does that mean? I need to first assume that firm 1 chooses a quantity, and now what would be the best response of firm 2? Okay? So suppose we are here. Suppose we are here, and now we want to see the best response of firm 2. How do we do that? We first find the best response of firm 2, as we did for the previous example. And so simply solve the maximization problem and get this reaction function. Now we reduce these infinitely many actions to just simply sum of them. And those are the star ones. Or as we used it previously, like these arrow ones. Okay, this would give you to R2. This would take you to R2. Now, firm 1 knows that if they choose any quantity, they'll be reacted by R2 as follows. So what they would do, they simply substitute R2 into their profit function, original profit function, and maximize their profit. How would it look like? It would simply be the substitution of R2 instead of Q2 in the profit function, and the best response would be simply the differentiation of that equal to 1. So if I substitute R2, I simplified it here. You can do it as an exercise for yourself, but you'll see that there will be some things that cancels here, and at the end you'll get something like that. 1 minus Q1, or in other way, say half minus half Q1 to the power of 2 minus half CQ1. Okay? Now if you differentiate that with respect to Q1, U1 with respect to Q1, you get minus Q1. 2 will multiply here and will be canceled, so it will be minus Q1 minus half of C. And that's where this Q1 star came from. Okay? So when we put this equal to 0, you will get this Q1 star. And this will be the best response of firm 1. Now, once we get the best response of firm 1, we substitute it to the best response function of firm 2 and get the best response of firm 2. So we simply substitute Q1 into that, and then we get Q2. Okay? Now let me again show you the difference of these two examples that it's a little bit confusing. Don't worry if you're mixing what I did in the last two examples. In the first example, we have two profit functions for each firm. Without the knowledge of the other firm's quantity, they do the maximization problem and find two reaction functions. Here, because the game is sequential, firm 1 moves first, and then firm 2 decides to choose their quantity. So we move backward. When we move backward, we say firm 2 would have a reaction function based off the choice of firm 1. Therefore, we find the best response of firm 2 as a function for any choice of firm 1. Now, since we have this reaction function, we will put it into the original profit function of firm 1 and maximize with respect to Q1. Okay? So this is totally different compared to finding two reaction functions and find their intersection. That was the Cournot equilibrium. Here we find one reaction function and put it into the original function of the profit function of the other firm and find the best response of the other firm. So, in other words, when I found the R2, I'll put it into the other firm's profit function and maximize, and then I find, for instance, this as the best response. And if you go through that direction, it will give you these two quantities. Okay? So, in other words, is Q star, this is Q1 star, and this is Q2 star. You know that there are many Q1 and Q2s here because they are continuous, but among those, we first chose the best responses of firm 2, and then the best response of firm 1, they will intersect in just simply one quantities for each firm. Now let's see how these two quantities differ from each other. As you can see, we had Q1 star equal to Q2 star equal to a third of 1 minus C. Here we have this equal to half and this equal to 1 over 4. So if, for instance, let's go with a number for C. Suppose C is equal to half. If C is equal to half, then here we have, so I would say C is equal to half. I mean, the reason I'm doing this is just I wanted to compare the quantities and show you the difference between simultaneous move and sequential move. So C equal to half, I'll get here 1 over 4. Here I'll get 1 over 8. Here I get 1 over 6. As you can see, a quarter is greater than this. And what does this mean? It means that the first mover has a strict advantage in those kind of duopoly games. So if I want to somehow replicate this with a real-world example, like Coles and Woolies compared to Costco, as you can see, there are much fewer number of Costcos in Australia compared to Coles and Woolies, and that is because Coles and Woolies were the first movers. Obviously, Costco could increase their quantity, but that would reduce both firms' payoff. So their equilibrium is somewhere that Coles and Woolies get more quantity and Costco get less. Of course, many things will change over time, so you may see that more stores will open over time, but in the one-shot game at the beginning, that's how you observe. Another example is Aldi. When they came to Australia, you remember that, I mean, many of you may remember, there were just few of them, but now over time, many things are changing, and then Aldi is now becoming a large group and gets a larger share of the market. So they will basically, the first mover advantage would vanish over time if the game will be continued over time. But at the beginning, there was a great first mover advantage for those which were existed in this market. And when players move simultaneously, obviously their payoff, their quantities would be somewhere between the first mover and the second mover. Okay? That's the Kono outcome, and these two are Stackelberg outcomes. Any question? Good. We are a bit ahead of time, so if you had any question, just please feel free to interrupt me. Okay? Great. So I'll spend more time on repeated games then. Now, let's go to our famous table at the beginning. So far, what we did, we wrapped up whole part of the complete information games. Nash equilibrium, mixed strategy, Nash equilibrium, subgame, perfect equilibrium, and that's it. The next move is obviously to go to incomplete information games. But before that, there's an extension here that is called repeated games. What is repeated games? Repeated games are those games that are repeat more than one stage. Why do we care about that? You will find it out in the next couple of lectures. First of all, let me explain to you what is a repeated game and what's the difference between a repeated game and a sequential game. A sequential game is where players move sequentially. So player 1 moves, and then player 2 observes, and then moves. That is called sequential game. But a repeated game is where the whole process that I just explained repeats once again. Okay? That would be the stage game, and repetition of the stage game will be called repeated game. Why repeated game matters? If you remember that we had many good payoffs in our games that were never achievable in simply one-shot game. We would see that there is a good payoff, but players would go to the worst outcome for both of them, like Prisoner's Dilemma. They go to a very bad outcome for both of them, and that is because the game is just repeated in one stage. What we're going to show here is that if a game repeats frequently, let's say, for instance, infinitely, then players may learn to collude with each other without communicating with each other and go to the better outcome. Okay? And that's what we observe in reality. In reality, for instance, we barely observe firms in duopolistic case fight with each other and the price goes to the marginal cost. What we usually observe is that they're cooperating with each other and the price is larger than marginal cost. And that is due to the repeated nature of the games that these guys play. And most of the games in reality are repeated games. That's another justification for us to have this part of the lecture in the game theory. Let's go to our preliminaries, and some of them are just what I said. Unlike the games that we studied so far, a repeated game have more than one time. It's repeated more than one time. The stage game is identically repeated several times. Now, strategies are conditioned on history of players. So, for instance, if two players want to play Prisoner's Dilemma several times, they remember that last time they didn't cooperate with each other, and they both got to prison for 7 years, for instance. Now, they may simply try to cooperate with each other and somehow continue with less term for both of them if the other person cooperates as well. So if it is mutually agreed without simply talk to each other, obviously, if this wasn't a non-cooperative game, they could call each other, talk to each other, and simply say, yeah, let's do that, and we both get better off. But this is a non-cooperative game. And an assumption of a non-cooperative game is that firms cannot, or players cannot communicate with each other. Okay? And in real world, if it turns out that two firms communicate with each other when they choose their prices, there will be heavy fines. And there are lots of regulators in Australia, for instance, that check that, although they may cheat in closed doors and no one would figure it out. But if one can figure out that, for instance, Shell and BP are cooperating with each other when they are choosing their prices, that will be millions of dollars of fines for those firms, because that is against the competition rule, and there are organizations in Australia that basically control that. So therefore, we are in a non-cooperative situation, because you might simply say, why would we bother repeating the game? They can simply talk to each other and say, let's play the best outcome. But that's not the case, and that's not an assumption in our model. So there's a history of the game, which we call HT. HT means the outcome at period T. Now, this is the outcome of this stage game at period T for a player, and then H capital is the set of all possible histories for all the periods that the game has been repeated. Let me again start with an example, and then we proceed to two different types of repeated games. Suppose there are two firms. This is a very famous example for repeated games. That is price competition. Suppose there are two firms competing in prices in a repeated game in discrete time. Discrete time meaning that, for instance, every day is discrete. Today, tomorrow, every week is discrete. This is how it works. Continuous time is, very complicated and not realistic. In each period, they both can set their prices either high or low. The payoffs are as below, denote A, I, T as price low or high. A is the action of firm I at time T. Now we have another element for the action, and that is the time. Previously we had action of firm I. It was either choose a price high or low. Now it is at time T. Either it's period 1, 2, or vice further, etc. A very good example of this case is, for instance, two service stations. Suppose there are two service stations next to each other in a street, and every day they need to just bring up the sign as their prices. Suppose they're not digital, the old system, they will only change the price once a day, and in the morning, simultaneously at 6 a.m., they will simply put a sign on top of their station that would basically be the price of their unleaded. Okay? So the service station knows that this game will repeat, because they're not planning to close. So from their point of view, this game will repeat several times. This is not just today. And we're trying to show that this will change things. This is not going to be the same as a single shot game where we assume that there are two service stations that leave only for one day. Okay? So the question asks us two things. If firms repeat this stage game T times, T is obviously assumed to be less than infinity. Oops, my infinity is 8. So if they play T times, meaning finite times, then find the SPE. Then second says, if firms repeat the stage game infinitely times, then show if the discount factor delta is 3, and then blah, blah, blah. Okay, so I don't want to bother you with this. We get to it. First of all, look at this stage game. This is the stage game. Firm 1 and firm 2 moves. The first thing you need to do is just assume it's just one shot and find the Nash equilibrium before you go any further. because I'll show you how important this is. And then once you found the single-shot Nash equilibrium, then we'll try to answer the question. First question says, suppose the game repeats in t times. T, we know t is finite. This means that we can draw the tree form of this game. How do we draw it? So the one-shot game will be firm 1 decides to choose between low and high, and then firm 2 simultaneously chooses between low and high as well. Okay? So there are payoffs here, 2, 2, 0, 5, 5, no, this is 0, 5. Low, high. This is 5, 0, 0, 5, and again 4, 4. Okay? Of course, this is not a symmetric game because this is 2, 2, and that is 4, 4. This means that when they both choose the high price, they'll get a high profit. But if one firm tries to choose a low price, the other choose a high price, the one that chose on a high price would lose a lot. Go back to my service station example. If one guy goes for $1.4, the other one goes for $1.3, and imagine these two are next to each other and it's identical. There is no reward and loyalty program. People have no preference over there. They will obviously go to the cheaper one. And then the high price one would lose a lot of money, get zero profit. But if they both decide to go with $1.4 a liter, then they'll make a lot of profit. Of course, there's another option. Both go with $1.3 a liter, which is the low price, and then they get the lower profit. Let's derive the Nash equilibrium of this game in one shot. So if player 2 plays low, what's the best response of player 1? To play low, because 2 is larger than 0. If player 2 plays high, the best response of player 1 is to play low. If player 1 plays low, the best response of player 2 is to play low. If player 1 plays high, the best response of player 2 is to play low. Okay, as you can see, the only Nash equilibrium of this game is low-low. And if these two service stations are supposed to live for just one period, we predict this would be the outcome. But now suppose they live more than that. Before I can proceed, let's come up with some more notations. Again, as you can see in examples and in problems, we don't use that much of notation, but these notations are necessary to define the equilibrium. So HT is the history of actions of players at each period at period T. So anything before period T happened is HT at period T. A strategy is a sequence of maps of SIT. Now we have an element T on a strategy, which is what you chose at period T. And there is a discount factor, delta less than 1, which players discount future incomes for today. So $1 I earn a year from now values to me lower than $1. Is that clear for everybody? This is a basic concept that I assume most of you know. So we discount future income by a rate lower than, weekly lower than 1. Is that correct? So for instance, if the interest rate is 0.4, we know that what $1 next year would value to us 0.96%. Okay, something like that. Of course, when the years go further, that'll be a bit more complicated, but I'll show you how to do that. So what we do is now let's not say that right now. So why do we discount? For two reasons. One, because of time preference. We prefer to spend today than tomorrow. That's all of us. We do that. The other thing is that uncertainty about future. So many people say, yeah, who knows what will happen next year? I may earn twice as more money I earn today, and I may not care about $1 as much as I care today. That's the concept behind borrowing and lending and the interest rate. So you borrow from banks and pay them interest because you value the money more today compared to tomorrow. Okay? So given that, whatever we just say, each period of the game that I described above, so suppose this is period 1, now period 2, I can draw exactly the same thing, and that would be period 2. Now period 3, I can draw the same thing, the same 3 I mean, and so on and so forth. Okay? Of course, I'm never going to ask you to draw a game 3 of a repeated game in an exam, but this is just helpful for the concept. Now suppose there's a period t at the end, so we know that the same thing will happen at every period up to period t, and we can draw the period t 3 and find the Nash equilibrium, and then everything will be the same up to the end of the game, because nothing changes in each of these periods. They're exactly the same. So if I find, for instance, this as the SPE or NE, let's be right. That's LL, the NE of the game. So that would be the same for the last period as well, because nothing will change till the last period. So therefore, the same best responses will remain at each period. Okay. Now this is another thing that you need to be careful. Now, having said that, what I'm going to do, the repeated games literature would divide into 2 major categories. One is the finite horizon repeated games, and one is infinite horizon repeated games. Whatever I just said is not doable for an infinite horizon game, because for the infinite horizon game, we don't know what would be the last stage, and therefore we cannot use backward induction. So that's basically the major difference between these 2 groups of games. And if you look at the problem that I just gave you, this one is a finite horizon game, and the other one is an infinite horizon game. Okay? So another point I should mention here is that the literature on repeated games is very huge, and in fact, repeated game is a course by itself at postgraduate level. Okay? It's a very large literature. But in this course, we don't want to do all of it. We just want to do those tiny things that are related to us, to our purpose. So if you wanted to read other literature and other textbooks regarding to the repeated games, be very cautious, because that may lead you to a wrong answer, and you may answer the questions in this course wrong. Okay? Be very careful, because here we just pick some parts of the whole massive repeated game literature, and we say, okay, this is it, and that's what we need to know for this course. So be very careful if you wanted to go to other literature, another textbook. Of course, you can ask me and tutors if you had any question and consent. So what we're going to do in this course is we're going to define only one proposition or one result at each of these 2 type of repeated games. So only one result for finitely horizon repeated games, and only one result for infinite horizon games. That's it. Nothing further. There will be many other results, but that's all we want in this course. Now, the general result that we're going to discuss so obviously, as you can see, this is a very messy thing. I mean, if one have multiple equilibria, then what would happen? So what we're going to do is to somehow use a general result for each of these 2 type of games and proceed with that. There's a general result in finitely repeated games, and it's very intuitive. You just need to somehow look at the intuition rather than just looking at the notation and techniques. Just look at the intuition. It simply says, if the stage game has this unique NE, then the unique SPE of the repeated game is the NE strategy of the stage game in every repetition. Okay? What does this say? This simply says that. Now try to, if it is finitely horizon game and it has only one NE, then if I want to go backward, of course I can go backward no matter how large T is, I can go backward. So, but if I want to go backward, I know what route to take, because there's only one route. And that route is the NE and at each stage game. So there's one NE here, one NE there, and one NE there. So therefore, the SPE of the game would be the repetition of NE at every stage game. Okay? Now, for this example, as you know, we have only one NE. Now we simply answered the first question. The SPE of this game is LL at every T. Okay? Again, there are multiple ways to write this. Just need to make sure that you write the correct set of strategy of the stage game. You can even write it in words. You can say each firm plays low price at every stage game of the repeated game. Okay? So this is for every, and this is T. T means time. So T is a subset of T, capital T. This means that the SPE of this game is playing LL at every period of T. Going up. Okay? This is the only general result that we're going to learn for finitely horizon games. So now if there are multiple equilibria, then things become so messy. And I don't expect you to know that in this course. Because when there are multiple equilibria, then there are multiple routes. It's like you are going through different cities, and each city has different type of streets. Okay? Suppose for the first case, suppose you are in a city in south, and there are identical cities up to your destination to north, and you know the best route for this city. You will take the same route in all of the cities. You'll find the best route to your destination. Okay? That's the definition of SPE when there's single NE. But now if there are multiple NEs at each of these cities, then it will be very messy. So, it's not, again, very difficult. Some people teach them at this level of the course, but I don't like them here because it could be very confusing for you. And we don't want to care about the results, but just let me tell you a little bit. So the routes simply tell you sometimes you can even deviate from Nash equilibrium in some of the cities, okay? Or in some of the, let's say, stage games. That's the difficult part. Otherwise, if it was just the Nash equilibrium, then we could simply say there are more SPEs, many SPEs. Okay, so now everybody happy with the general result in the finitely repeated games? So one thing we know, if there's a single NE, that would be the SPE of the finitely horizon repeated game at every stage of the game. Okay? So from now on, if I gave you an example and ask you to repeat it for T periods and find the SPE, you just need to first find the Nash equilibrium of the single shot game. If there were multiple Nash equilibrium, your answer would simply say, we don't know the SPE, there will be many SPEs. If there were single Nash equilibrium, your answer would be the SPE of the game is the repetition of the Nash equilibrium at every stage game. Okay? All good? So now, things become more difficult when this game repeats for infinite horizon. I want you to all be okay with the finite horizon game before I jump to the infinite horizon game. If you have any question, just please ask right now. Okay. So now, infinite horizon game is the part B, part 2 of the question, is this part. When we ask to repeat this game infinitely, the example of the service stations that I told you is one example. So if you own a business, unless it's in a very weird situation, you never have a deadline for your business, okay? You know that this is going to be an ongoing business unless it bankrupts. So therefore, you don't have a end date for your, let's say, actions and strategies. Whenever you choose a price today and your competitor chooses a price today, you guys know that this will continue at least as long as we know, okay? So there may be unpredictable stop dates for these two, but at this stage we assume that this will continue forever. Therefore, there won't be a deadline at the end such that we can go to that and use backward induction to come up and find the SPE. So nobody can use the same method as I just did here to find the SPE of an infinite horizon game. So what we do for the infinite horizon games is using, again, another established result, but I first show you how to find this in the example that we just gave you, and then I give you the definition of the result. That makes things much easier. But suppose I'm trying to do the following. Suppose firms know that if they cooperate forever, they'll all get better off. Okay? Because looking at the example, you know that 4, is larger than 2, 2. Okay? So what they do is as follows. They say, okay, let's play high as long as the other firm plays high in all previous histories. Otherwise, we go low. Okay? Before I continue, we didn't use discount rates for finitely horizon games, at least in this example. It wouldn't matter because of the result that we discussed, which was only a unique equilibrium. Even if there was a discount rate, nothing would happen. Both payoffs would reduce with equal amounts, so nothing would change. But for infinite horizon games, we will use the discount rate, okay? Because the horizon is infinite, and $1 100 years from now may value close to 0. Therefore, we need to discount the payoffs in order to make sure that we are comparing correct amount of money. So what I was saying by now here is that we no longer are able to use the backward induction, but we use a trigger strategy. A trigger strategy is a strategy that ideally makes both firms better off if they cooperate with each other. So the service stations say we put a high price on the board as long as there's no history of low price for the other firm. And if the other firm suddenly decides in one period to cheat and shift to a low price, then we'll punish both ourselves and them by choosing low price for the rest of the years that we're going to ever play this game together. Okay? Now, why would firm 1 cheat? Obviously, there is an incentive for cheating. If there weren't an incentive for cheating, then high would become a Nash equilibrium. Okay? Remember, the reason that high did not become a Nash equilibrium was these 5s. Because when one firm plays high, the best response of the other firm is not to play high as well. It is to play low and get a larger profit. Okay? So if this firm plays high, then the best response of player 1 is to play 5. So if these 5s didn't exist, then obviously 4 would become a Nash equilibrium, and we didn't have this discussion right now. The reason we have this discussion is that there is a cheating element in these games. Now, those firms that wanted to cheat in a trigger strategy, they say, okay, we'll get 5 for one period, but then we'll be punished for the rest of the periods, and the other firm will never ever trust us. So we have to get 2 for the rest. Now, let's see if this deviation would give us higher payoff than cooperating for the rest of the game. Okay? Of course, for different discount rates, that would lead to a different answer. If the discount rate is very high, then I would prefer to cheat right now, get 5, and then forget about 4s tomorrow, because tomorrow the value of a 4 is much lower. But if the discount rate is small enough, but the discount rate is small enough, then you may simply use the trigger strategy. Did I say the reverse? Yeah, if the discount rate is larger than the threshold, you won't have, you will have incentives to maybe cheat. I mean, of course, this depends on the difference between 5 and 4 as well. If the cheating would result in a very large payoff, then the cheating becomes more, let's say, tempting to each firm. Now let's see how do we need to do that in terms of mathematics and formalization. The trigger strategy we find is as follows. We say AI plays high if there is no low in the history of the game. Okay? In exams, you are free to write this rather than in words rather than write it like that. You'll get the full mark. It doesn't matter. What we care is that you understood the correct thing. You can simply say AI or the trigger strategy is to play high as long as there's no history of low in previous periods. Otherwise, play low. Okay? I mean, of course, there are two actions here. So otherwise means playing low in at least one period. And if the other firm plays low in one period, we're never going to trust them again, and we're going to play low for the rest of the game. Now, we need to compare. This would result to two different directions. We need to compare the payoffs of these two and see which one is greater than the other one in order to be able to somehow find the SPE of the game. So, therefore, this would create two types of subgames. One subgames that firms have low prices in the histories, therefore there will be one high price and then low for the rest. And the other subgame is that firms play high in all the histories. Okay? The question is to see whether these two payoffs can result in larger quantities. Now here we need a little bit of background in mathematics, and that's called geometric series, finding a sum of a geometric series. If you don't know it, if you don't simply like it, you can simply memorize it here. It's not difficult because we don't switch it that much and that frequent here. So why do we say the geometric series? Because the way the discount rates are multiplied by the payoffs will form a geometric series till infinity. And we need to have this sum in order to be able to compare the payoffs. Because if I just write it this way, I won't be able to compare it with any other number. We need to know what would be the sum. And given that delta is less than 1, less or equal to 1, I mean, let's say this must be less than 1 in order to have this. Because 1 would result to denominator being 0, and that is negative. So let's say less than 1. So now let's see what would be the payoff or the sum of the payoffs of these two trigger strategies. So if player 1 and 2 decide to play high at every period, they'll get 4, 4, 4 for the rest of the game. So the payoffs will be 4 in period 1, 4 in period 2, 4 in period 3, and until infinity. Okay? Now we want to discount these numbers and see what would be the sum. So in period 1, obviously 4 will not be discounted because it's current period in period 0, obviously. In period 1, it will be discounted by this discount factor to the power of the period, which is 1, times the payoff, which is 4. In period 2, it would be 4 times delta to the power of 2, and vice versa, etc., till the end. Remember that since delta is less than 1, when we take it to power of a larger number, it becomes a lower number. So when we take a number less than 1 to the power of n, the larger the n, the lower is the whole thing. Okay? Because this is a smaller than 1 number, multiplying it to itself for several times will reduce to a smaller number. So therefore, this series, we know it will merge to 0. So thanks to mathematicians, we know that this series has an equivalent. That is equal to 1 over 1 minus delta. So there's one very important point here is that you can factorize the payoffs. So you can simply write this as follows. 4 times 1 plus delta 2 plus blah, blah, blah. Okay? Because 4 is common in all the terms. And from mathematics, we know that this geometric series has the following sum. Okay? These are the only two things that you need to know in this course regarding to the mathematics background for the geometric series. Nothing further. And this thing is sometimes handy for the trigger price for the other strategy, and this thing is handy for the cooperation strategy. So therefore, if we factorize 4, then we know the sum will be 1 over 1 minus r. So multiplying that, this would give us the sum of the payoff for one firm if they cooperate with each other. Now, let's see what would this firm get if they cheat. Okay? Now, suppose you want to cheat, and you know in any period if you choose a low, then for the rest of the game you will get low. But in that particular period, you'll get high number of customers and you'll get a high profit. Now, if you want to do that, you're better off doing it at the first place. So if there's any history of high and cooperation before, we simply eliminate that because it's an infinite horizon game. So we start with a trigger strategy where at first period, one of the players simply cheat and choose a low price and get 5, and then for the rest of the game, they'll get punished and get 2. So the other, I didn't write it in my lecture notes. I should have wrote it here. But maybe I decided to write it in the class. So that trigger strategy that I just told you would result into 5 at period 1 plus 2 delta 1, 2 delta 2, and so on and so forth. Okay? Is that clear for everyone? If you want me, I have time to explain it more. One period, low price, when the other firm chose the high price, then I'll get punished for the rest of the game, and I have to go with low. Okay? So we want to find the sum of this payoff as well, and then compare it to this guy and see which one is larger. And obviously this would depend on delta, and then for some deltas, the other one will be larger, and then we could say this would be the SPE of the game. Now, finding the sum of this is simply 5 plus, again, factorize 2. Now you have delta plus delta 2 till infinity. So this is the same as the other series that I just showed you. And the sum will become equal to delta over 1 minus delta. Okay? So remember, some of the lecturers at the same level, they don't even bother to explain geometric series. They assume that everybody knows it and they just simply go forward. Okay? So, but the reason I'm saying this is just, it is not a rocket science. You just need to know two sums. And that is, when it starts with 1, the sum would be 1 over 1 minus r. And when it starts with delta, the sum would be delta over 1 minus delta. Okay? So now we have 2 payoffs. One is this, which is the payoff of cheating. And one is this, which is the payoff of cooperation. We want to see what are the deltas that give us higher payoff for cooperation. So we'll assume this is larger than that. So if you simplify that, so multiply both sides by 1 minus delta. I'm assuming, again, you know these kind of algebra. If you don't, just come to me or to your tutors. We'll explain it to you. Multiply both sides by 1 minus delta, and then take delta to one side, everything else to the other side. You get delta greater than 1 over 3. So if delta is greater than 1 over 3, then cooperation can be supported as the SPE of this game. Okay? So therefore, in infinite horizon games, the way we represent the SPE is by this trigger strategy, something like that, and then add a delta. So we first introduce a trigger strategy, then we compare the payoffs of the cooperative compared to non-cooperative strategies, and then we find the delta that is representative of larger amount for the cooperation, and then what we say is that we can support the trigger price and the cooperation as the SPE of the game as long as delta is larger than that amount, which is here 1 over 3. It makes sense because if delta is too large, so your payoffs, remember here, your payoffs are getting smaller and smaller in future. I mean, your payoffs are very small in future because you're getting a large number right now and small numbers in future. If delta is large, these numbers are relatively become smaller and smaller in future, and they get closer to zero. So therefore, this number, these becomes larger, and you have more incentives to cooperate with each other rather than cheat. Now, if delta is very small, say equal to 0, this is the most extreme case, then all other numbers except the first one will become 0. So then you just care about today's money the most. Okay? Therefore, you simply try to cheat and get 5 because you don't care about future money. Okay? So now it's time to read the established result for infinite horizon game. This would help you to find trigger strategies. The established result simply says that any feasible payoff equal or higher than NE of a stage game can be implemented in the SPE of an infinitely repeated game. Okay? So before I start doing anything here, doing anything here, once I found that there is a unique NE, and I saw that there is a higher payoff for both players compared to the NE, I knew that there will be a trigger strategy that I can support this new strategy as the SPE of the infinite horizon game. Okay? So of course we don't bother with the proof of these theorems. This is a very famous theory in repeated games and in economics as well. But what we care is the result. From now on, if you have an example and you know that you see that there, in that example, that particular example, there are a set of payoffs for both players that are larger than the NE, and they are not the NE of the stage game, you know that you will be able to find a trigger strategy that can support that strategy as an infinite horizon SPE. Okay? So how do we find trigger strategies? Note that if you have an NE, and if you have a payoff that is larger than NE for both players, there must be a cheating element somewhere. Okay? What do I mean by cheating element? I mean there must be some other payoffs for one player in the same action that is larger, and that would basically result in the two larger payoffs not becoming the mutually best responses. Okay? Otherwise, for instance, if I look at this game, there are two NEs here. This one, I don't want to bother finding them. You should be very comfortable doing that by now. I know that this 5-5 is not an NE. But why is that? It is because of these sevens. Okay? So now how do I design a trigger strategy? I'll design a trigger strategy by saying as follows. I say the larger payoff played always, as long as there's no history of the cheating payoff. In this case, let's not say a payoff. The larger payoff, the strategy for that larger payoff played for every period of the game, as long as there's no history of the strategy of the cheating payoff. Here, the strategy of cheating payoff is to play D when the other firm plays C. Okay? Therefore, if there's no history of D, then that would result to a trigger strategy that is playing cooperation for the rest of the game. So let me not jump to the solution of this game and then first read the game, because it could be a bit confusing to you right now. It's a bit different. That is, the following example is called a modified version of Prisoner's Dilemma. It is an extension of that, and now players have three actions: to defect, to cooperate, and to be partial. Say something partial is that somehow say confess some of the whole things. Okay, not very bad things, not irrelevant stuff. So half confess. In that case, this is the payoffs. So if you confess half of this stuff, you'll get, again, not a bad sentence, but still not as good as the case that you cooperate with each other. So here we use different type of payoffs. As I told you in that session of prisoner's dilemma, people use different ways of representing prisoner's dilemma. So of course, sentencing to a prison can be a negative payoff, but you can normalize it to 0, and saying becoming free is a positive payoff, something like that. But at the end of the day, what matters is that cooperation would result to the highest payoff, and confession would result to the lowest payoff for both firms. Okay, and that's the case here. So as you can see, this game has two Nash equilibria. One is DD and the other is PP. The question is, suppose this game is played in two periods. What would be the SB of the game, or can the players do better? So what would be your answer? If this game is played in 2 periods, what would be the SB of this game, or is there any SB that both players do better? You don't know the answer. Because, as I said a couple of slides ago, we only know how to answer finite horizon games when there's only one and E. Okay? So, of course, it is nothing out of what we learned here. I can do it here for you, and you will all understand, but I just don't want to confuse you, because it would go through a different result and different strategy which we have not learned yet. So, since there are multiple Nash equilibria, we don't know whether there is an SB in a finite horizon game which do better than the NEs. Okay? That's it. Now, the question is, what about the infinite horizon game? Is there any delta that we find such that we can support CC being played at all periods? That's the question we're trying to answer for the rest of today's lecture. So the trigger strategy I define here is that suppose players play C in all periods as long as there is no history of any other action. Or let's say there is no history of D. Because there is no reason for the other player to do anything else, because obviously D has the highest payoff for them. They may go partial. That would be a different trigger strategy. So let's focus on the following trigger strategy, and that is players cooperate for the rest of the game as long as there's no history of defect or confession. So if there wasn't a history of defect or confession, then you'll play defect for the rest of the game. Now, we are comparing two simple routes of payoffs. One of that simply gives us 5 at all periods. That's why we write 5, 5, 5 for the rest of the game. The other one gives 1, 7, and 0 for the rest of the game. Okay? Because once you cheat, you get 7 for one period, and then for the rest of the game, you get 0, because the other player will never trust you and will play defect for the rest of the game. Here, finding the sum is much easier, because when there is a 0, then all of these will become 0. So the sum of the defection strategy will become 7. The sum of the cooperation strategy would become 5 plus 5 delta plus 5 delta to the power of 2, and so on and so forth. So that sum we know will become equal to 5 over 1 minus delta. What we want is 5 over 1 minus delta becoming larger than 7. As long as this is the case, then players will not have incentives to cheat or defect, because they know cooperation would result in a higher payoff for them for the rest of the game. So again, there will be a little bit of math and calculation here, which results into delta being larger than 2.07. So if delta is larger than 2.07, we can support the trigger strategy as the SV of the game. So this will be the way you solve these problems. You will start with a trigger strategy. The trigger strategy simply tells you play the best payoff, the best NE payoff. Remember, we are in this zone, and this zone simply says that if there is a feasible payoff equal or higher than NE, which is not an NE, it can be supported in the SP of the finite infinity horizon game. So therefore, in trigger strategy, first find the best payoff for both firms that is not an NE, and make that the repetition of the whole game as one strategy, as long as there is no history of cheating. Okay? Of course, there must be, again, I repeat this several times because it's very important. There must be some element of teaching, otherwise that payoff, that set of large payoffs will become a Nash equilibrium. Okay? What I mean here is that there must be these sevens, otherwise this 5-5 would become the Nash equilibrium. The reason that the 5-5 didn't become a Nash equilibrium is because when, for instance, player 1 plays cooperate, player 2 has a better payoff by playing defect. Okay? So therefore, one part of the trigger strategy is to play larger payoff for the rest of the game, the strategy that represents the larger payoff for the rest of the game. The other trigger price is to play the worst payoff or the Nash equilibrium as long as there is a history of cheating. Okay? So this would give us two sets of payoffs with respect to a discount factor. You find the sum based on this formula, one of these two formulas, and then put the sum of the original trigger strategy, that is the cooperation, larger than the other one. So when you assume that the cooperation is larger than the other one, you'll get the delta that satisfies this equation. And one delta you found would be the solution of the SB of that game. And the way you represent it is simply as follows. The trigger strategy is the SB of the game for this set of deltas. Okay? So the trigger strategy you introduced at the beginning is the SB for those deltas. Okay? I repeat once more. You start by introducing the trigger strategy. Then that trigger strategy would give you two directions of payoffs. One is cooperation, the other is cheating. Compare those payoffs for different deltas and put the cooperation payoff larger to find those deltas that give you higher payoff for the cooperation. And then those deltas will be the solution of your problem for that particular trigger strategy. Okay? Because for those deltas, you'll always get higher payoff for cooperation compared to cheating and deflection. Any questions? Okay. So now, the next step is games of incomplete information. And that is what we're going to do next week. I don't want to confuse you more. I guess this is, right now, usually this lecture is the peak of the game theory. And I feel that most of the students find it the most difficult part. And in some sense, I can say one of the biggest peak of the course as well. We get to some peaks later on in contract theory, but I don't think it would be as high as this one. So things will be smoother, much smoother from next week. And the good thing about repeated games is that it is entirely separate from all other analysis that we studied. So you can simply ignore repeated games, and you can still get a high distinction from this course. That's the way I designed it. Okay? Of course, you'll get a high mark if you simply learn repeated games. But let me explain, we have time, let me explain why am I doing that. As I told you, I have different groups of students here. Some of them try to study further to PhD. Some of them want to go to industry. So I need to make both of them happy. When you want to apply for a PhD, the first thing is a PhD coordinator of the university do is will look at your micro and macro marks and whether they are high or no. When they are high, they simply, because the assumption here is that the course was easy, so they simply contact the course coordinator. The story that I'm telling you has happened in the last 4 years several times. They contact me and say, okay, what was your course? What did this student get to, for instance, get a high distinction? Then I explain what I taught them, and then they will understand that this course was a serious one and it wasn't an easy one. And at the same time, those who don't want to further study to PhD would be easily able to get good marks and pass the course, also even get an even distinction or high distinction without doing the sophisticated part. So you may expect, I mean, you can see again in the library in previous exams, I don't want to, I mean, there's nothing to spoil. We had a very difficult question in the final exam that was for repeated games in either Cornell or Burton competition, prize competition. And those students who can answer that, I can support them for any PhD program or even any industry job they want. And so far I had a student at very good universities in Australia because of, I cannot say because of that, but of course that was a very important reason for that. So I had students with a scholarship at UNSW, ANU, UQ. They are all now PhD students. And in most of the cases, I guess all of them except one situation, the PhD coordinator contacted me directly either via email or a phone call and asked me what was the materials in this course and how did these guys were assessed. And I could defend them. So at the same time, so don't be worried about these topics. At the same time, I want to make those happy who want to study further and those who want to somehow go to industry and continue with something which is not technical in future. Okay? The longest story short, don't panic. This will not be the whole part of the course. Okay? Good luck. See you next week.
Yeah, those are the things that are more complicated.